Ever wonder what an atom really looks like? Not the simple, spherical model you've seen in textbooks. Today, we're diving into the quantum mechanical model, a mind-bending world where electrons aren't particles, but waves of probability.
Electron configuration is a shorthand notation that indicates the arrangement of electrons in an atom orbitals. It follows specific rules and principles. To understand electron configurations, we need to grasp the concept of quantum numbers. These numbers describe the properties of electrons in an atom. The principal quantum number n determines the energy level or shell of an electron. Also indicates the energy shell, or how far from the nucleus an electron is, and how high the energy is. The outer shells have the highest energy. As a rule, atoms always fill up their low energy shells first and work their way out. Energy shells are divided into subshells called angular momentum quantum number labeled as L, which is further divided to subshells called magnetic quantum number labeled as ML. Together, quantum numbers n, L, and ML specify an electron's orbital, another word for its location in the electron cloud.
Principle governing electron configuration. So we have three principles, which are the Aufbau principle, Pauli extension principle, and Hans rule. So Aufbau principle is electron fills orbitals starting from the lowest energy level to the highest. And the Pauli extension principle is no two electrons in an atom can have the same set of 4 quantum numbers. And the Hans rule is within a subshell, orbitals are filled with 1 electron each before pairing up.
Writing electron configuration. To write the electron configuration of an element, we use the following format: 1:2, 2:2, 2p6, 3:2, 3p6, 4:2, 3d10, and 4p6. The number before the letter represents the principal quantum number or energy level, and the letter represents the angular momentum quantum number or orbital shape. Then lastly, the superscript indicates the number of electrons in that orbit.
Atomic orbitals, the quantum mechanical picture. In the quantum mechanical model of the atom, electrons don't orbit the nucleus in fixed paths like planets around the sun. Instead, they exist in regions of space called orbitals. These orbitals represent the probability of finding an electron in a specific region around the nucleus.
There are 4 primary types of orbitals, each with a distinct shape. S orbitals, these are spherical in shape. P orbitals, these are dumbbell shaped. D orbitals, these have more complex shapes, including cloverleaf and dumbbell shapes, with a donut around the middle. And lastly, the F orbitals. These have even more complex shapes and are typically found in higher energy level.
Periodic trends and atomic rad. Atomic radius is a measure of the style of an atom. It's generally defined as half the distance the nuclei of 2 identical atoms bonded together. Two primary trends influence atomic radius across the periodic table.
So first is across a period left to right, decreasing atomic radius. As we move across a period from left to right, the atomic radius generally decreases. Increase nuclear charge. The number of protons in the nucleus increases, leading to a stronger positive charge. Constant energy level. Electrons are added to the same energy level. Effective nuclear charge. The increased nuclear charge pulls the electrons closer to the nucleus, reducing atomic size.
Down a group, top to bottom. Increasing atomic radius. As we move down a group, the atomic radius generally increases. Reason: increased energy levels. Each successive element adds a new energy level, which is farther from the nucleus. Shielding effect. Inner electrons shield outer electrons from the full nuclear charge, reducing the effective nuclear charge on the outermost electrons. Greater electron repulsion. As the number of electrons increases, the repulsion between them also increases, causing the electron cloud to expand.
The quantum mechanical model has revolutionized our understanding of the atom.
It's a complex and fascinating world, but by breaking it down into a smaller piece, we can appreciate beauty and power.
So the next time you look at an atom, remember it's not just a simple sphere, it's a dynamic, probabilistic cloud and electrons.